Hello everyone, and welcome to the first lecture in this tire mini-series. In this lecture, we're going to focus on what goes on inside a tire as far as forces and thermodynamics are concerned. This material is critical to begin moving on to more advanced topics such as modeling and analysis, so let's get right into it. Key concepts are going to be springs and friction. This should hopefully be a review for everybody, but if it's not, please check the links in the description for some resources to see these things. Also, do note that the arrow above certain variables indicate that these are vectors with magnitude and direction. First, on the left, we have Hooke's law, F equals kx, a pretty straightforward equation for a spring which outputs a certain force based on a certain deformation. For a basic spring, we can assume a linear spring stiffness. However, if we're looking at a conical or beehive valve spring, then k might not be a simple constant, but a function of deformation as well. Next, we have standard friction, which works mathematically in a similar way to Hooke's law. However, now instead of a deformation, we have a normal force. You can think of this normal force as a clamping force, which holds two surfaces together. It is also worth noting that mu, our dimensionless friction coefficient, is not a simple constant. Rather, it is a piecewise function with a different value based on if two surfaces are sliding or not. Looking at rubber, in short, it comes from the sap of a certain tree. It takes quite a bit of processing before it is ready to be a tire, but it's still worth understanding some basic things about the material. First, it is a viscoelastic material, similar to a memory foam mattress. When it is deformed, it takes it a little while to spring back to its original shape. The visco in viscoelastic is short for viscous, like a viscous damper. So rubber has internal dampening. This means that as it relaxes from an input strain, it releases heat. Moreover, the rubber is an insulator, both electrically and thermally. Thermally, it likes to hold on to heat and not give it away to the surroundings. Looking at the construction of the tire, after we process the latex, the rubber goes through the manufacturing process where it is mixed with other synthetic elastomers, vulcanizers, composites, and metals to construct the tire that we now know. At this point, it is important to understand the components of the tire. Looking at this diagram from Bridgestone, we have the bead, the belt, the tread, the sidewall, and the body ply. For most thermal modeling, we can group together everything but the tread into the term carcass. Not pictured, of course, is the inflation gas, which in most motorsport series is pure nitrogen. Also worth pointing out that the tread patterns are almost entirely used for water displacement. Racing tires for dry weather typically have no tread pattern in order to maximize the amount of contact area between the rubber and the road. So now let's talk about how the rubber-road interface actually generates grip. First, we have mechanical grip generation. This is almost identical to meshed gears, but tiny. Every surface has a level of roughness to it, and the squishy rubber can get in between these little peaks and valleys and grab onto it, propelling the vehicle forward. This mechanism accounts for about 20% of generated grip. The remaining 80% actually comes from van der Waals adhesion bonds. While this may sound scary and reminiscent of chemistry, it's really just glue. You can think of the racing tire almost like a roll of double-sided tape. The rubber in the tire literally glues itself to the road, but only in the dry. These bonds are almost entirely eliminated if the road has water, oil, or some other contaminant on it. Hence, the tread patterns we discussed earlier are designed specifically to get water out of the contact patch. Now, changing into modeling mode, let's look at our tire forces. Vertical forces are massively important to the generation of grip. Why? Because grip is just friction. So if we maximize our normal force, we can generate more tire forces and get around the racetrack faster. The primary forces acting normally on the tire are the aerodynamic downforce, the weight of the car, and the weight transferred during maneuver. There's also the effects of springs and dampers, but we won't deal with that just yet. Importantly, the rolling radius seen here in blue decreases as normal loading increases. This is called tire squash. We can see that as the tire squashes, we build a bigger contact patch. Longitudinally, we have our regular radius and the angular velocity of our rotating tire. The angular velocity can be interpreted as a vector going into the page. Now, if we take the cross product of these two vectors, we get the velocity of the rolling wheel. As our wheel rolls along by the generated friction force caused by the rubber meeting the road, we note that the velocity of the wheel is usually not the same velocity as the rolling car. This inequality leads to something called slip. We measure slip using the slip ratio, which is defined in equation 3. Now, we can think of our slip ratio as a deformation, and with an appropriate stiffness, we can rebuild Hooke's law for longitudinal force. At this point, I beg you to pause the video and think to yourself, what would cause the velocity of the wheel to be greater than the velocity of the car, and vice versa? How does one quantity being greater than or less than the other affect the formula for slip ratio and longitudinal force? Let's use this same concept to develop lateral forces. Assuming now that you've unpaused the video, here we have a noticeable deformation occurring. We have the tire pointing in one direction, but traveling in another. This may seem abstract at first, but it's important to remember that our tire is not a rigid body, but more of a squishy one. This deformation is called the slip angle, and I'm going to pause here quickly to talk about our usage of the word slip. We typically think of slip as a surface that is slippery, but that's not really the case here. I personally believe that we should call this something else like deformation angle, but I don't make the rules, so slip angle. Regardless, we have a slip deformation angle and a parameter C, called our cornering stiffness. Once again, this is just Hooke's law. This is a good time to talk about camber and what it accomplishes. If we're looking at the car from the front, we can see that our tire kind of leans inward a bit. This is on purpose, and it's to generate camber thrust. When the tire is set down on its corner, it wants to spring back. This effect can be used to help with cornering by generating roughly an additional 10% of lateral force. In parallel to most engineering systems, this does come at a trade-off. Too much camber can make a tire prone to failure by overloading the sidewall, and this does take away contact patch area on straight lines, hindering acceleration and braking performance. Last but not least, we have our aligning moment. The mechanics of this are a little vague, but bear with me and let's build this up. We're looking at a contact patch that's rolling up on the screen. Next, we're going to apply a small force right in the center of the wheel. By Newton's third law of motion, the contact patch will create a reactionary force that is equal to and opposite in magnitude from our applied force. This force, however, is just a little bit off center and below the line of action of our applied force. This causes the generation of a clockwise moment, which will eventually align the lines of action of V wheel and F applied. The distance between F applied and F reaction for FSAE tires is typically close to 1 inch, so it's not a very large moment, but it may be necessary to include for more advanced vehicle models. Now, thermodynamics. Finally, as alluded to earlier, it is essential to recognize the tire as a thermal system. This is an image I borrowed from one of my sibling students and my PhD supervisor, who does a great job highlighting all the different heat flows within the tire. This is all based on work done by a gentleman named Daniel Patrick Kelly. I recommend you pause the video to fully digest what's going on here. Qs 1, 2, and 5 are heat flowing into the tire, while Qs 3 and 4 are heat being released by the tire. Interestingly, there's no heat flow into the inflation gas within the tire. In reality, there is, but it is at a very small rate. The heat that enters the inflation gas is almost exclusively caused by the brake rotors. In the next video lecture on tires, we will talk about testing and modeling your tires, as well as introducing you to some further resources for your own education.